So I'm not sure what's going on. I think it might be my internet. It's not working. So I think I'm gonna read the solutions. It's cutting up. I'm gonna read the solutions for other people here, other projects. And maybe watch some videos about relativity, special relativity. So basically, this project is they give you a bunch of data about housing prices somewhere, and then you have to predict the sale price using these data points. So this doesn't contain the code, I guess, for his solution. So this is from my understanding now, the solutions from other people. I've looked at a couple of them, but there's 81 columns and close to 1500 rows. So you think they are iterating through the columns. I don't know what numeric does. I guess makes all the values numeric. Then he's dropping the ID column, which I think is the first one. I'm not sure where target comes from. I'm not sure if I understand this part here. DF target, drop an A, handling missing data. So I guess here they are looking for all the columns that have missing data. This sums up all the columns that it returns a series with the future, which is a column, and the amount of new values there each column has divided by the shape of the column, which is the number of columns, I think. And it's going to locate this on the data frame. Then it sorts, then it's sorting by values, sorting values, which returns a series of those columns. And it's doing all this on the figure thing. So pretty much creating a graph of all the columns that have missing values. Let me put some music. Hopefully it's not too loud. Then he's dropping the values, the columns with a lot of new values. The way that I did this is by creating a filter with lock and then creating a loop to drop them. A for loop. I'm more interested in the machine learning part of the thing. Yeah, then this creates a heat map of the correlations. So this method here gets the correlations of all the how correlated the futures in the thing are on the data frame. I'm not sure what this does. Maybe I should look it up. Return the indices for the upper triangle of R, which in this case is mask, which is this thing here. Return an array of zeros with the same shape and type as a given array. So he's creating a frame, I think, to draw the heat map from. So it's creating an array with the same shape of the correlations matrix, which is this here. Then he's taking the half of the array, half of the frame. No, oh, I got it now. He's using this to take the other half off. So he's creating the blank part here. And I'm not sure why exactly he's doing that, but yeah, I spent a lot of time trying to create a loop to print graphs like this, but It wasn't working when I was doing, and I'm not sure why. It was printing all the graphs uh, in only one graph. It didn't work, so I had to do it manually. So it's looping from 0 to the shape of the rows of the index of this column here, where it's correlated features. Oh, target is here, sale price. Now I understand. So target is sale price. So here, yeah, he's dropping the new values of sale price column, which I didn't do, I think. I followed the instructions of the book, and the book told me to replace with the medium, the no values with the medium of the each column. So that's what I did. Maybe I should open my solution to compare. On the machine learning part, I just copied some project just to look at later. I didn't make any submissions. OBS disconnected. Yeah, so it was in correlations that I was looking at the thing. Let me go back to this part here. Correlated here. So he's taking the absolute correlation with output variable. So he's taking the correlations in relationship to the target, which is sale price. So he's getting the correlation between all the other futures and sale price. And this is gonna return a series with the column and the correlation that they have with each of them. So the higher this number is, the more correlated the futures are. And if it's a negative, it's less correlated and goes from 0 to 1, which is what I did here. This gets the correlation. Then I started with sales price, then created the frame. Then I used this filter here and attached to this variable. And then I put it on this list here and created a scatter matrix for them. And I remember somewhere that I Also, yeah, here. I guess it was for, yeah, for the new values. This loop takes off the columns of the data frame that have more than 1,000 new values, because the data frame has 1,500, so 1,000 is a lot. But the thing that I wasn't being able to do is I tried doing this loop here to print a map, to print the correlation between futures, but it wasn't working. Let me do this. So this, I did it, I ended up doing manually. So you can see like, it's like this, all of them. But if I run this here, oh, I need to see what is count. Count. Yeah, count, select the types is gonna select the numbers of the data frame housing, which in this case is df. Oh, now it's working. That's weird. No, just that's just the idea. Oh, it works. Oh, that's strange. First time that I did this, it was showing me some graphs of a bunch of colors. Uh, so my assumption was that it was putting stacking all the points in one graph in each of the graphs, but it seems to be working now. So maybe there's something wrong with the other way that I did it. Or maybe I'm just tripping. Let me comment all of this out and try it out here. That's really strange. Maybe I fixed it and I don't remember. So this is making a graph of the log, and let me see what happens if I don't use the log. I remember I was having a bunch of, I spent a bunch of time trying to figure out, and for some reason, my stuff wasn't working. So I've looked at some videos and did it the other way then. But I was still having some issues from what I remember. But now it seems to be working. So I don't know what's going on. Whatever. And I didn't do this. Remove outliers. I think that it makes sense from from what I saw so far on machine learning. They usually tell you to remove outliers, and it makes sense because if you don't, it's really hard to find patterns in the data because you can't predict something that is unpredictable. But I think that there might probably be a better way to do this because oftentimes outliers are the things that have the biggest impact in some situations. So you can't. I think there might be, maybe it already exists, but I'm not sure. I haven't discovered. But there might be a method that is better to do things than just removing outliers. Like a method that figures out the probability distribution, the likely probability distribution of some event, and then updates the probability based on new data coming, and then it just extrapolates the prediction taking into account the probability of some outliers happening. Something like markets, for example, you can't remove outliers from markets because they're gonna happen more often than a normal probabilistic distribution. And oftentimes those outliers are the difference between winning and losing, and that's why it's so hard to make money by trading. So I think he did it manually here by comparing each row. For in range, then it's creating a graph of the rows on the correlated future index. So correlated futures is the graph, or is the series or data frame. So this gives the absolute value of the correlation between sale price and other futures. And then here is filtering for those that have more than 0.05 correlation. This is what correlated futures is. Then he's getting the index and the rows 0 to 6, which I guess is the first 6. Maybe it's columns instead of rows. It's probably columns. So the first 6 columns. And then he's creating a bunch of graphs for the correlation between the sale price, and the futures that have higher correlation. Selecting categorical futures. This is the part that I stopped on my own project. I tried doing a little bit, but I didn't finish. So he's getting the sum of the null values on the categorical futures. And then he's filling it with 0, I guess. I don't know what this does. Get the mode of each element along the axis. The mode of set of values is the value that appears most often. It can be multiple values. Oh, yeah. So he's replacing with the value that appears more often in the rows. Replacing the null values with the value that appears more often. Which makes sense because you can't uh, substitute by the mean if it's a categorical value. And you don't want to change the data too much. Then he's selecting the columns of the data frame here that are strings or no non categorical that are categorical columns and searching for the new values, new columns, null columns. So I think he's checking to see if he substituted all the values. Maybe I should write this down. This mode thing. I think I'm gonna copy this. And I'm gonna save on my own to look at later. I'm gonna go to the bathroom right back. think I'm gonna look at the rest of this solution and one more solution. Then I'm gonna watch the videos on the special relativity playlist. So this is the same library that the course, the tutorials we're talking about, I think. Oh, it wasn't on the previous one. I think I'm gonna skip through the machine learning part, the thing. So he's using his boost regressor. I think it's XGBoost, the name of the library, which the other guy from the solution that I saw before also used. I think I'm gonna look this up because I don't know. I see it a lot, but I don't know what it is. And I think the guy in the book mentions it briefly. Cross-validated grid search over parameter grid. So it's basically used to see if it's underfitting or overfitting. One of the techniques used to test the effectiveness of a machine learning model is also a resampling procedure used to evaluate a model if we have a limited data. So it's basically cross-validating the model here. The first part of this. Oh no, this is the whole code. So it usually looks like that the machine learning part is usually the easiest part, and most people just implement some library to do it, which makes everyone probably give the same predictions roughly. The only difference is the way that they filtered the data, they cleaned the data. So I think understanding the way that these libraries work and the machine learning algorithms work can give you an edge if you're able to create something new, which obviously might be really hard. Otherwise, everyone would be doing that. So he creates these parameters here, and estimators max that random state learning rate. Learning rate is from arbitrary, I guess. Random state is probably arbitrary as well. I haven't studied this method yet, but max def is probably arbitrary as well. I think all these parameters are just selected by him and not the data. And then it just strings, and then so why is the data from sale price a copy of the data from sale price? Then he passes the test set, X train, X test, Y train, Y test. And here's the shape of the test, the train and the test. Then he fits the data on the training set and tests on the test set. Uses the model to predict the test set. So I guess fitting means that the you're using the regret minimization technique on the data points of the train set. I think I'm gonna look at another one and then watch the videos on the playlist. So these guys separated everything previously, categorical and numerical, and the new values of each one. And he's using the same library as the other guy here to normalize the data. So first he's normalizing, then so here I guess it's showing the normalization process. Goes from this to this, which is a lot of difference. So sale price doesn't follow a normal distribution. It makes sense because the economy follows a Pareto distribution. So house prices should follow the same or very similar distribution. since they are determined by markets. Then he's finding the correlation, doing the same thing the other guy did, and then maximum likelihood and multivariate variate imputation. Now he's removing the no values. God damn. And I think for this means Kane's nearest neighbors for the machine learning part. I think the way that this works is you guess it's kind of like the distribution of mass, finds the distribution of mass, quote unquote, the data point, the data set. But I haven't looked at it yet, so I'm not really sure how it works. Since there is a strong correlation of some of the garage variables with the response, we can investigate the correlation of garage futures to avoid non-optimum inputting. That's another thing that people talk about, that you should drop futures that are highly correlated with the result. But I don't really understand the reason behind that. Yeah, I guess makes it. Yeah, I'm not sure. Because intuitively for me, it seems that you should want highly correlated futures for trying to predict something, because those are probably the futures that are going to be the most indicative of the result. They're going to tell you the most about the results you're looking for, the thing that you're trying to predict. But Maybe the reason why is because it increases the chances of overfitting the data when you use high correlated features. But yeah, that's probably the reason why people drop high correlated features. But I don't know. Maybe there's a better way to do it. I think I'm gonna watch the videos now, the playlist.
We'll also derive the famous equation E equals mc squared. In special relativity, we found that different observers disagree on many physical quantities like time, space, velocity, momentum, and kinetic energy. In previous videos, we found that all inertial observers agree on the speed of light in a vacuum c and the spacetime interval s squared. In this video, we're going to introduce the idea of Minkowski vectors, also called 4 vectors, which are vectors in spacetime that all inertial observers agree on. In standard Newtonian physics, we're used to dealing with three-dimensional vectors, which in this video I'm going to denote using small lowercase letters. We have three-dimensional position, small r, which measures the x, y, and z coordinates of a point, and also velocity, small u, which is the derivative of position with respect to time, momentum, small p, which is mass times velocity, acceleration, small a, which is the second derivative of position with respect to time, and force, small f, which is the derivative of momentum with respect to time, which is also mass times acceleration if the mass is constant. In special relativity, most of these quantities aren't very useful because the time variable is measured differently in different reference frames. This means that every frame will take time derivatives with respect to a different time variable. Recall in the last video that we defined the spacetime interval s squared between two events. When s squared was positive, we said s is equal to the speed of light c times the proper time tau, which is the time between two events when they happen at the same position. So tau is agreed on in all inertial reference frames. Since all frames agree on the proper time tau between two events, they will also agree on derivatives with respect to tau. We can now define Minkowski vectors, or 4 vectors, which are denoted with big capital letters, using derivatives with respect to proper time tau. We start with the 4 position, big S, which is the 4-dimensional position in space-time. For velocity, big U, is the derivative of 4 position with respect to proper time tau. For momentum, big P, is mass times the 4 velocity. For acceleration, big A is the second derivative of 4 position with respect to proper time. And for force is the derivative of 4 momentum with respect to proper time, which is also mass times 4 acceleration if the mass is constant. We're going to find that all reference frames agree on these 4 vectors because they are invariant. Recall the idea of invariance from Relativity 102. If we write the same vector in terms of different basis vectors, we get different components. We've already seen this idea with the spacetime separation vector S, which is also called 4 position. And we can change between the components of S in different reference frames using the Lorentz transformation. In this video, we'll see that this is also true for any 4 vector, including 4 velocity, 4 momentum, and others. We can write the same geometrical vector with different components in different reference frames, and change between the components using Lorentz transformations. Now, our starting point for all these Minkowski vectors is the four-position big S, which gives us the position of an event in spacetime relative to the origin. Big S has one time component, ct, and three space components, x, y, z. We can get the four-velocity, big U, by taking the derivative of four-position with respect to proper time tau. To calculate this, we expand big S into its components. Since we have the derivative of a sum of terms, we can just give the derivative operator to each individual term. Now normally, we would take one of these four derivatives and do product rule with it, getting a term with the derivative of the components plus a term with the derivative of the basis vector. However, in the case of inertial reference frames, basis vectors are constant everywhere in spacetime, so the derivative of a basis vector is 0 for inertial frames. In future videos, when we deal with non-inertial frames, we're going to see that these derivatives of the basis vectors are actually non-zero. But for this video, we're dealing only with inertial frames, so the derivative of the basis vectors are 0. So the derivative of four-position S is another four-dimensional vector containing derivatives of t, x, y, and z, with respect to proper time tau. We can take the speed of light in a vacuum c out in front of the derivative because it's constant. Let's figure out what dt by d tau is. Recall the Lorentz transformation between a coordinate system ct tilde and x tilde to another coordinate system ct and x. Here, beta is just the fraction of the speed of light, u over c, and gamma equals 1 over the square root of 1 minus beta squared. Recall that the proper time tau between two events is the time measured between events in a coordinate system where the events happen at the same position. Let's say in the frame ct tilde and x tilde, these two events happen at the same position, so x tilde equals 0 between these two events. So given the Lorentz transformation equation for time, this means that if we set x tilde is equal to 0, then the time t tilde is equal to the proper time tau, because it's the time between events measured at the same position. So this term goes to 0, and we can cancel c from both sides to get t equals gamma times tau. So taking the derivative of t with respect to tau, we just get gamma. So we've determined that dt by d tau is gamma, and this helps us determine the first component in ds by d tau. But what about the x, y, z derivatives? Well, if we recall chain rule from calculus, if we have nested functions where t is a function of tau and f is a function of t, we can calculate the derivative of df by d tau by multiplying df by dt and dt by d tau. As an example, we can consider x of tau instead to be a nested function x of t of tau. We can then turn dx by d tau into dx by dt times dt by d tau. Of course, dx by dt is just the familiar velocity in the x direction we know from non-relativistic Newtonian physics. And I'll denote this velocity by small u with superscript x. And we already know from before that dt by d tau is just gamma. So the derivative of x with respect to proper time tau is just the ordinary x direction velocity times gamma. We can use this chain rule approach for all derivatives of space coordinates with respect to proper time, and this gives us the ordinary non-relativistic velocities with respect to the t coordinate times dt by d tau, which is just gamma. If we factor out the gamma that appears in every term, we see that the four-velocity ds by d tau equals gamma times the vector cet plus uxex plus uyey plus uzez, where the lowercase u denotes the non-relativistic velocity. So the derivative of the four-position s with respect to the proper time tau gives us a new four-vector called capital U, which is the four-velocity. The components of the four-velocity u are given by big UT, big UX, big UY, and big UZ. Remember, small or lowercase u denotes non-relativistic velocities with three components x, y, z with respect to t. The big or uppercase U denotes relativistic velocities with four components t, x, y, z with respect to proper time tau. We can also write the four velocity in array notation, with basis vectors in a row and the vector components in a column. If we multiply the arrays, we get first entry times first entry, second times second, third times third, and fourth times fourth, which gives us the original vector big U. So what's so good about this four velocity vector big U? The answer is that big U is invariant in all coordinate systems. Let's see this using an example. Let's say that Einstein is stationary in space in a space-time diagram, and a car is moving off to the right in the x direction at half the speed of light. So the non-relativistic velocity in the x direction, ux, is 1/2 c. For simplicity, let's say that the velocities in the y and z directions are 0, so we're only concerned with the x-axis and the time axis. The square of the total velocity of the car is normally ux squared plus uy squared plus uz squared, but since only the x velocity is non-zero, this means that the total velocity u is ux, which is 1/2 times the speed of light. This means that beta, which is u over c, is just 1/2. And for beta equals 1/2, the corresponding gamma coefficient is 2 over the square root of 3. The four velocity vector of the car has only two non-zero components, gamma times c for time and gamma times ux for x direction. Subbing in 2 over root 3 for gamma and 1/2 c for ux, and cancelling these 2's, we get that big U equals 2 over root 3 cet and 1 over root 3 cex. We can see that the components of this four velocity vector match up with the direction of the car's world line in our space-time diagram. However, in the reference frame of the car's 3 velocity is 0, and this means that beta equals 0 and therefore gamma equals 1. In the car's frame, the car's 4 velocity equals c times et tilde. All of the space components are 0. Again, this matches up with the vector big U in our space-time diagram. So we can see that the four velocity vector big U is an invariant vector. It has different components in different reference frames, but it is the same unchanging vector in space-time. Also, notice that even though the car's ordinary non-relativistic velocity is 0 meters per second in its own reference frame, its four velocity is not 0. The car still has a non-zero four velocity vector component in the time direction. It's just that the spatial components of the four velocity are 0. Also, just as the components of the four position vector can be transformed to different frames of reference using the Lorentz transformation, the components of the four velocity vector can also be changed to a different frame using a Lorentz transformation. When we have a four velocity vector written in a basis in array notation with a row of basis vectors and a column of vector components, when the basis changes with one Lorentz matrix, the components change with the inverse Lorentz matrix. So the components of the four velocity vector big U transform just like the components of the four position vector big S. We can see that if we take the Lorentz transformation, plug the gamma and beta coefficients in, and also the ut and ux components in Einstein's frame, we get the expected four velocity components of ut tilde equals c and ux tilde equals 0 for the car's reference frame. But these components still describe the same four velocity vector u. Another thing to notice is that the quantity big U dot big U is also invariant and agreed upon in all reference frames. Recall that with a Minkowski orthonormal basis, the time basis vector dotted with itself gives +1, and a position vector dotted with itself gives -1, and mixed basis vector dot products are 0. So in our case, big U dot big U is ut squared minus ux squared. In Einstein's frame, this gives us 2 over root 3c squared minus 1 over root 3c squared, which is 4 over 3c squared minus 1 over 3c squared, which ends up just being c squared. In the car's frame, we can take this same formula and plug in the four velocity components for the car, which are c for time and 0 for x. This gives us the same result, c squared. It turns out that big U dot big U is equal to c squared for all four velocity vectors. All four velocity vectors have a Minkowski length of c, the speed of light in a vacuum. If you want to go through the proof, you can pause this video, but the basic idea is to write big U dot big U in terms of a basis, then distribute the terms, calculate the dot products, sub in the formulas for the U components, factor out gamma squared, and then do some canceling, and we get c squared. So the Minkowski length of all four velocity vectors is c. So we've learned that the 4-velocity vector big U is just the derivative of 4-position big S with respect to proper time tau, and these are its components, and its Minkowski length will always be c. Let's take a look at another 4-vector, the 4-momentum, capital P, which is defined as the mass times the 4-velocity vector big U. This is similar to the definition in Newtonian physics, where 3-momentum equals mass times 3-velocity small u. If we expand the 4-velocity big U, we can see the 4-momentum big P written in a basis with components. So in some basis et, ex, ey, ez, the components of the 4-velocity look like this. And to get the components of the 4-momentum, we just multiply by the mass m. Now, I should say that anytime I refer to the mass m of an object, I'm referring to the mass when measured in its own reference frame. Some textbooks call this the rest mass, but I'm just going to call it mass. Now, I will warn you that some textbooks use a definition called relativistic mass, which I've written curly m, defined as gamma times the rest mass. Remember, since gamma is always greater or equal to 1, this means that the relativistic mass will increase with velocity. Now, the reason that some physicists came up with the idea of relativistic mass is that it makes the components of the 4-momentum vector look more like the Newtonian momentum that we're used to, where the spatial components of the 4-momentum are now just the relativistic mass m times the ordinary 3-velocity. However, it's my belief that we should try as much as possible to write relativistic equations using invariant quantities that are the same in all reference frames. So in this video series, I will not be using relativistic mass since it changes in each reference frame. Anytime I talk about mass, I'm talking about the rest mass of an object that is agreed upon in all reference frames. So looking again at the 4-momentum components, the spatial components of the 4-momentum look pretty familiar. They are just the Newtonian momentum, mass times velocity, but multiplied by the gamma factor. However, the time component of the 4-momentum, gamma times mass times the speed of light, looks more mysterious. To understand what gamma times m times c is, we're going to have to expand gamma as a Taylor series in terms of beta. Recall that the Taylor series of a function f of x is an infinitely long polynomial in x that approximates f of x. You might already be familiar with the Taylor series of e to the x, sine of x, and cosine of x. It turns out that the Taylor series for gamma as a polynomial in beta looks like this. If you want to prove this, you can calculate the coefficients by taking derivatives of gamma with respect to beta and then evaluating them at beta equals 0. Now recall, beta is just a fraction of the speed of light, u over c, so we can sub that in now for beta. And if we take the time component of 4-momentum and multiply it by c, we get m times c squared times gamma. If we expand gamma using the Taylor series that we talked about above, we get this. We can distribute the mc squared to each term in the series. Let's ignore the first term for now. In the second term, we see that we can cancel c squared on top with the c squared on the bottom. And the higher order terms in the series are not too important for now. So we found that we can write c times the time component of 4-momentum like this. The second term in the series is the familiar kinetic energy from Newtonian physics, 1/2 times mass times velocity squared. This seems to imply that all these higher order terms are new kinetic energy terms that Newton didn't know about. Note that because of the u over c terms in here, these terms only become noticeable at speeds close to the speed of light, so it makes sense that Newton wouldn't have known about them. And finally, the first term doesn't contain any velocities at all, so it must be an energy that all massive objects have, even when they are at rest. So really, we found that c times the time component of 4-momentum gives us an energy term. It's the rest mass energy, mc squared, plus several additional kinetic energy terms. In other words, energy divided by the speed of light c gives us the time component of 4-momentum. So we now know the formulas for the 4 components of the 4-momentum vector. The time component equals energy divided by the speed of light, and the space components equal the Newtonian 3-momentum, mass times velocity, times the gamma factor. Also, since we know that the 4-velocity dotted with itself gives c squared, it isn't hard to calculate the 4-momentum dotted with itself. We just get m big U dotted with m big U, which is m squared times big U dot big U, which is m squared c squared. We also know that we can calculate the dot product of 4-momentum with itself using the Minkowski metric, where the time component squared gets a positive sign and the spatial components squared get negative signs. We already know from above that big P dot big P equals m squared c squared, and the time component of the form momentum is energy over c, and the position components are just the three momentum components multiplied by gamma. Now we can multiply all terms by c squared to get this, then move this momentum term to the other side of the equation to get this. And this is Einstein's energy-momentum relation. It relates the quantities of mass, energy, and momentum together in a single equation. Now, one special case of this formula is for stationary particles, when the non-relativistic momentum, mass times velocity, is 0. In this case, the formula reduces to the famous equation E equals mc squared. Remember, this only applies for stationary particles. Another special case is the case of a massless particle. If m equals 0, the above formula seems to imply that energy is also 0. But we know that light, which is massless, definitely carries energy, since the sun's light heats the Earth, so something must be wrong here. It turns out that the formula mass times 4 velocity doesn't work to get the 4 momentum of light. The reason is that the 4 velocity big U is not well defined for light-like position vectors. The proper time tau for light-like position vectors is always 0, so it doesn't make sense to take a derivative with respect to tau for a light-like position vector. And if we try to define the components of a 4 velocity vector big U for a light-like trajectory, we end up with ut equals plus or minus ux, so we get multiple solutions for what the 4 velocity components could be. So there really is not a good way to define what the 4 velocity is for light. So let's try to come up with a different way to define what the 4 momentum is for light. We know that the 4 momentum for light should be a null vector with a 0 Minkowski length. And this makes sense because the light's mass is 0. This means that the square of the time component of 4 momentum is equal to the sums of the squares of the position components for the 4 momentum. Now, we know that the time component of 4 momentum is equal to energy over c. And I'm going to write this combination of the squares of the spatial components of momentum as just big P with the subscript light to indicate the momentum of a light beam. So for light, which is massless, the energy of light comes from its momentum, not its mass. And if you know some quantum mechanics, you'll know that light's momentum is related to its frequency, where higher frequencies give higher momentum and energy. So we've managed to define the 4 momentum both for massive objects and massless objects like light. Let's take a look at how the 4 momentum vector is invariant by looking at our example with stationary Einstein and the moving car. We already know the 4 velocity vector of the car in each of their reference frames, so we just multiply that by mass to get the car's 4 momentum. Note that in the car's frame, the car's 4 momentum only has the time component and no spatial components. The time component is the car's energy. Since the car doesn't view itself to be moving in its own reference frame, its energy is completely in the form of rest mass energy, E equals mc squared. According to Einstein, the car is moving. We can see that the car does have some momentum in the x direction. The time component of the 4 momentum, the energy, has also increased, because gamma is greater than 1 for a moving object. This means that the car has both rest mass energy and kinetic energy from its motion. But in both cases, the mass of the car is constant and unchanged. Even though Einstein sees the car with more energy, he also sees it with more x momentum, which has a negative sign in this formula, and the extra energy cancels out with the extra x momentum to leave the mass constant. It's the same rest mass that the car would observe in its own reference frame. But why do we care about the 4 momentum? One of the reasons 4 momentum is so important is because 4 momentum is conserved. If you recall Newtonian physics, the law of conservation of momentum tells us that if we add up all the 3 momentum vectors of objects before a collision and add up all the 3 momentum vectors of objects after a collision, then the results should be the same. For example, if 2 particles with equal momentum in the x and negative x directions collide, their total net momentum is 0. This means that their total net momentum after the collision must also be 0. In special relativity, since we found that energy and momentum can mix together when we change reference frames using a Lorentz transformation, if we want a proper relativistic conservation of momentum law, we must use 4 momentum vectors, including both energy and momentum. Let's look at an example of 2 objects colliding together from opposite directions on the x-axis. After the collision, the objects will stick together. The first object has 4 momentum p1 with 5 energy units and plus 3 x momentum units moving to the right. The second object has 4 momentum p2 with 5 energy units and negative 3 momentum units moving to the left. The resulting object after the collision must have 4 momentum p3 that equals p1 plus p2. This means that p3 has 5 plus 5 equals 10 energy units and 3 minus 3 equals 0 x momentum units, so the object is stationary in space. However, the 4 momentum of the resulting object is not 0 overall. It still has 4 momentum in the time component, which measures its rest mass energy. Interestingly, if we calculate the mass of each of these objects using the mass-energy-momentum relation, the total mass of the objects before the collision is 4 plus 4 equals 8 mass units, but the mass of the particle after the collision is 10 mass units. This shows us that in special relativity, the rest masses of individual objects is not a conserved quantity before and after collisions. We need to remember to look at conservation of 4 momentum as a whole instead, not just conservation of individual rest masses. So we've seen that the derivative of 4 position s with respect to proper time tau gives us the 4 velocity u. It's probably not surprising that if we take the second derivative of 4 position, which is the first derivative of 4 velocity, we get another vector called the 4 acceleration, denoted by capital A. Now, I'm not going to go into a ton of detail with 4 acceleration because I'm actually going to cover acceleration in special relativity in great detail in the Relativity 105 videos, so you can watch those videos to learn more. But I'll do a quick derivation of the formula for 4 acceleration, and you can pause the video if you want to look at it. To take the derivative of the 4 velocity, we use product rule to get 2 terms, one with the derivative of gamma and the other with the derivative of this vector. The vector derivative is easy if we use chain rule on the tau derivative to get the t derivatives times gamma. The derivative of the first component goes to 0, and the rest gives us the non-relativistic acceleration 3 vector small a multiplied by gamma. For the other half of the product rule, the derivative of gamma with respect to tau can be changed to d gamma by dt times dt by d tau using chain rule. And since this is just the definition of the 4 velocity again, the complete formula for 4 acceleration is d gamma by dt times big U plus gamma squared times little a. It can be shown using chain rule that d gamma by dt is gamma cubed times little a dot little u all over c squared, with a minus sign in front. Now, the reason that this minus sign is here is because I chose to use the mostly minuses convention for the Minkowski metric, where a position basis vector dotted with itself gives a -1. Because of this, the formula axux plus ayuy plus azuz is actually the negative of the little a vector dotted with little u. If we had used the mostly pluses convention, where a position vector dotted with itself gives +1, then this negative sign would be a plus sign instead. So this is something to keep in mind if you see this formula in textbooks or websites, with a different sign convention. So this is the formula for the 4 acceleration, and if we like, we can write out the components of the 4 acceleration as a sum of 2 column vectors, which gives us this. So the formula for the 4 acceleration vector is actually quite ugly. The most interesting thing about the 4 acceleration, big A, is that it is not necessarily parallel to the 3 acceleration, small a, in the spatial dimensions x, y, z. If the dot product small a dot small u is non-zero, then the 4 acceleration components in x, y, z actually get another term in addition to the standard 3 acceleration, small a. So we now have 4 velocity, 4 momentum, and 4 acceleration. The last vector we'll talk about is the 4 force, capital F, which is the rate of change of 4 momentum with respect to proper time tau, where 4 momentum is equal to mass times 4 velocity. If we assume mass is constant, then we can pull mass in front of the derivative, and the derivative of 4 velocity we know is just the 4 acceleration big A, which we've already calculated. So the famous equation F equals ma is actually 4-dimensional in special relativity. It's worth noting that the time component of the 4 force vector is the derivative of the time component of momentum with respect to proper time. Since the time component of momentum is energy, this is the derivative of energy with respect to time, which is power. So the time component of the 4 force is a power term. So in summary, in this video we learned about several 4 vectors in special relativity that all inertial frames agree on. We started with the 4 position, big S, which in previous videos we called the spacetime separation vector. And this can be used to give us a notion of proper time tau when we take the Minkowski length of a time-like 4-position vector. We learned about the 4-velocity big U, which is d big S by d tau, and we learned that the Minkowski length of the 4-velocity vector is always the speed of light c. For massive objects, the 4-momentum big P is defined as mass times the 4-velocity. The time component of the 4-momentum is energy. However, for massless particles like light, we have a special definition where the particle's energy equals its momentum times the speed of light. The 4-acceleration big A is the second derivative of 4-position, and it is not necessarily parallel with the non-relativistic 3-acceleration in the spatial dimensions. And finally, we have 4-force, which is the derivative of 4-momentum with respect to tau. The time component of 4-force is power. All of these 4 vectors are invariant. The geometric vectors themselves are agreed upon by all inertial reference frames, but their components will look different in different inertial reference frames. In order to change between the components of these 4 vectors in different frames, we can transform the basis vectors using a Lorentz transformation, and transform the vector components with the inverse Lorentz transformation, just like we saw with the 4-position in previous videos. We know that this is possible for all 4 vectors because all 4 vectors are written in terms of a spacetime basis. And remember, basis vectors and vector components are 2 sides of the same coin. When we change our spacetime basis in one way, the 4 vector components will change in the opposite way because vector components are contravariant. So anytime we change our spacetime basis using a Lorentz matrix, we know that we can change the components of any 4 vector using the inverse Lorentz matrix by the rules of contravariance and covariance. You may have heard before that
I think I'm understanding, kind of understanding. I wouldn't be able to derive them myself, but I think I'm being able to keep up roughly with the explanations.
So today's topic is frequency, which means there will be so many terrible overused frequency puns that it hurts. Before we get started, don't forget to click the subscribe button and to click the little bell to get notified every time we post a new video. We'll get started with a super meta science reminder of the day. Everything around you is a signal that you can measure and use in some way. So today we're going to be talking about frequency, one of the biggest tools you can use to describe those signals that are happening in the world around us. The definition of frequency is pretty simple. A frequency is the number of times that something, literally anything, happens over a period of time. Think of the word frequent. A higher frequency means something is happening more frequently. If you go to the
The issue is, how do you define when something happens?
bathroom 3 times in a 1-hour class, that's a frequency, and also a sign that your teacher needs to be a little more entertaining. If you jump on a bed
Because it always depends on the subjective
250 times in 7 minutes,
observer.
that's a frequency too. To make things easy, it's most common to use the standard unit, hertz, hence my bad puns, to describe frequency. Hertz are nice because they're defined as 1 per second. So if I jump on a bed 3 times in 1 second, I jumped at 3 hertz. For now, it's important to remember
That's
that
why
frequency
the second question here, relationship between frequency and computation.
describes a repetitive pattern or event, like jumping up and down, turning off and off the light, Tom Brady scoring touchdowns. Sorry, I was raised in Boston, I have an excuse. There are ways to describe events that don't repeat using frequencies, but that's something for a later video. Now that we have the basic concept under our belts, let's make this a little bit more interesting. If frequency is the number of times an event happens per second, or 1 per second, that means that frequency is the inverse of the number of seconds it takes for something to happen. Therefore, if we take 1 and divide it by our frequency, we get a measurement called the period. To jump back to my bathroom break example, if you go 3 times in an hour, that period is 20 minutes, the amount of time between each bathroom break. The period measurement is also super useful. For example, if you jump on a bed or make an LED blink 5 times per second, which is 5 hertz, how long is the wait between blinks? The answer is the period of the signal. In this case, 1 divided by 5 hertz, which is 0.2 seconds. So all you have to do is remember that frequencies describe repeating patterns, and period is the measurement of how long one repetition takes from start to end. Okay, so let's get a little bit mathy for a second here. Rolling up the sleeves for the math. Let's say that a street lamp is flickering at 10 hertz. That means it blinks 10 times each second. 1 divided by 10 hertz gives us a period of 0.1 seconds. In a slightly harder example, now the lamp blinks on for 1 second, then off for 3 seconds. So what's the new frequency of the blinking light? In this case, it's easier to calculate the period first, which is 1 second on plus 3 seconds off, giving us 4 seconds. So if our period is 4 seconds, all we have to do is divide 1 by 4 seconds to get a frequency of 0.25 hertz. Frequency is actually something you've probably seen or heard.
Probably not going to be able to find the answer to exactly what I'm looking for, but because probably nobody knows.
What is frequency and common examples of frequency? Before starting the lecture, click on the subscribe button and get access to 100 of unique and simple lectures for free. Firstly, let me teach you about the basic philosophy of frequency. Consider Mr. P and Mr. Q. Let Mr. P eats 10 bananas in 1 second and Mr. Q eats 8 bananas in 1 second. Thus, the banana eating frequency of Mr.
With frequency probability. Frequency and probability is probably the same thing.
P is 10 Hz and the banana eating frequency of Mr. Q is 8 Hz. The winner is Mr. P because he eats 10 bananas in 1 second and its frequency is 10 Hz. Secondly, consider dog X and dog Y. Let they both run around the circular path. Now which one is running fast? Well, consider that dog X can run 2 times around this circular.
Okay, let's discuss the difference between frequency distribution, probability distribution, and normal distribution. What is frequency distribution? Frequency distribution is a table that displays the frequency of various outcomes in a sample, while probability distribution is a table or equation that link each outcome of a statistical experiment, while the normal distribution, commonly encountered continuous probability distribution. In our next discussion, we will find out what be the image and what is the difference between these three. Okay, so number one, let's find out what is a frequency distribution. Okay, if I have this one,
Identifying cause and effect. Identifying cause and effect in texts is important as it helps us to understand the events that are happening. It helps us to understand what's happening and why it's happening. A cause happens first. It's why something happens. To find the cause, ask, why did this happen? An effect happens after the cause. It tells us what happened. Let's look at some cause and effect relationships. It rained. Carolina got wet. It raining is the cause because it must have occurred first, and because it tells us why Carolina got wet. Carolina getting wet is the effect because it had to have happened after the cause, and it tells us what happened. Here's another example. Phil stayed up late. Phil was tired in the morning. Let's start by looking for the cause, which happens first and tells why. That's right, Phil staying up late. Which happens after the cause and tells us
I have this article right here from WebMD, and the point of this isn't to poke holes at WebMD. I think they have some great articles and they have some great information on their site. But what I want to do here is to think about what a lot of articles you might read or a lot of research you might read are implying, and to think about whether they really imply what they claim to be implying. So this is an excerpt of an article, and the title of the article says, "Eating breakfast may beat teen obesity." So they're already trying to kind of create this cause and effect relationship. The title itself says, if you eat breakfast, if you eat breakfast, then you're less likely or you won't be obese. You're not going to be obese. So that the title right there already sets up this, that eating breakfast may beat teen obesity. And then they tell us about the study. In the study published in Pediatrics, researchers analyzed the dietary and weight patterns of a group of 2,216 adolescents over a 5-year period from public schools in Minneapolis, St. Paul, Minnesota. And I won't talk too much about this. Looks like a good, sample size. It was over a large period of time. I'll just give the researchers the benefit of the doubt, assume that it was over a broad audience, that they were able to control for a lot of variables. But then they go on to say the researchers write that teens who ate breakfast regularly had a lower percentage of total calories from saturated fat and ate more fiber and carbohydrates. And to some degree, than those who skipped breakfast. And to some degree, this first sentence is obvious. Breakfast tends to be things like cereals, grains, you eat syrup, you eat waffles. That all tends to fall in the category of carbohydrates and sugars. And frankly, that's not even necessarily a good thing. Not obvious to me whether bacon is more or less healthy than downing a bunch of syrup or Fruit Loops or whatever else. But we'll let that be right here. In addition, regular breakfast eaters seemed more physically active than their breakfast skippers. So over here, they're once again trying to create this other cause and effect relationship. Regular breakfast eaters seemed more physically active than their breakfast skippers. So the implication here is that breakfast makes you more active. And then this last sentence right over here, they say over time, researchers found teens who regularly ate breakfast tended to gain less weight and had a lower body mass index than breakfast skippers. So they're telling us that breakfast skipping, this is the implication here, breakfast skipping is more likely, or it can be a cause of making you overweight or maybe even making you obese. So the entire narrative here, from the title all the way through every paragraph, is look, breakfast prevents obesity, breakfast makes you active, breakfast skipping will make you obese. So you say, like, boy, I have to eat breakfast. And you should always think about the motivations and the industries around things like breakfast. But the more interesting question is, does this research really tell us that eating breakfast can prevent obesity? Does it really tell us that eating breakfast will cause someone to become more active? Or does it really tell us that breakfast skipping is correlation? So the whole point of this is to understand the difference between causality and correlation, because they're saying very different things. Causality versus correlation. Causality versus correlation. Obesity correlates with breakfast skipping. We're seeing it at the same time. Activity correlates with breakfast, and breakfast correlates with activity. That all of these correlate. What they don't say, and there's no data here that lets me know one way or the other, what is causing what, or maybe you have some underlying cause that is causing both. So, for example, they're saying breakfast causes activity, or they're implying breakfast causes activity. They're not saying it explicitly, but maybe activity causes breakfast. Maybe they didn't write the study that people who are active, maybe they're more likely to be hungry in the morning. Activity causes breakfast, and then you start having a different takeaway. Then you don't say, wait, if you're active and you skip breakfast, and I'm not telling you that you should. I have no data to do that. Maybe you'll leave a little.
I think everything is correlated. The issue is that if you don't know the nature of true events, if it's just probability, how do you determine which one causes the other one?
You lose even more weight. Maybe it's even a healthier thing to do. We're not sure. So they're trying to say, look, if you have breakfast, it's going to make you active, which is a very positive outcome. But maybe you can have a positive outcome without breakfast. Who knows?
Which means time only exists after observation, which might be the definition of time. But then how does that relate to awareness, and how does that, what is the moment that is born, is the question.
Likewise, they say breakfast skipping, or they're implying breakfast skipping can cause obesity, but maybe it's the other way around. Maybe people who have a high body fat, maybe for whatever reason, they're less likely to get hungry in the morning. So maybe it goes this way. Maybe there's a causality there.
Because we can say that observation is the electromagnetic field. So if that's true, then the nature of the electromagnetic field should determine the direction of time and the cause and effect relationship between things. Which means that you can go back in time, but only from another perspective where that's possible because of the nature of the electromagnetic field. But then you would have a question of why the nature of the field is the way that it is now and not any other way. And it has to do with awareness. But then you get into this paradox of the higher problem of consciousness.
There, or even more likely, maybe there's some underlying cause that causes both of these things to happen. And you could think of a bunch of different examples of that. One could be the physical activity. So physical activity, and these are all just theories. I have no proof for it, but I just want to give you different ways of thinking about the same data, and maybe not just coming to the same conclusion that this article seems like it's trying to lead us to conclude that we should eat breakfast if you don't want to become obese. So maybe if you're physically active, that leads maybe when you are physically active, that leads to you being hungry.
So from the law of the relativity from the previous, I think that it shows that energy is correlated with mass, and energy is the frequency, where frequency is defined by observation. And I don't think anyone knows where observation is born. How do you measure that? It's always dependent on the subjective nature of the experience from which events are happening, which already assumes a cause and effect relationship because that's the essence of experience.
hungry in the morning, so you're more likely to eat breakfast. And obviously, being physically active also makes it so that you burn calories, you have more muscle, so that you're not obese. You are not obese. So notice, this isn't, if you view things this way, if you say physical activity is causing both of these, then all of a sudden you lose this connection between breakfast and obesity. Now you can't make the claim that that somehow breakfast is the magic, if you find someone's obese, maybe the rule here isn't to force a breakfast down your throat. Maybe
I'm gonna
In
rush
the
to the
modern
bathroom, right back.
world, we humans are completely surrounded by electromagnetic radiation. Have you ever thought of the physics behind these traveling electromagnetic waves? The great scientist Heinrich Hertz was the first man to transmit and detect electromagnetic waves. In his famous experiment, a high-voltage current was applied to the two ends of two metal wires, which generated a spark in the gap between them. This spark resulted in the radiation of electromagnetic waves. Those electromagnetic waves traveled through the air and created a spark in a metal coil located over a meter away. If you had placed an LED in that gap, the bulb would have glowed. This was a clear case of electromagnetic wave propagation and detection. However, before Hertz, the brilliant mathematician James Clerk Maxwell had already laid out the foundations for electromagnetic radiation by formulating 4 mathematical equations. However, these equations and the Hertz experiment raised a question: how do electromagnetic fields detach themselves from wires and propagate through a space? More specifically, what we need is a traveling electromagnetic wave and not a fluctuating one. Let's explore this logically. Consider an electric charge, which is moving at a constant speed. The electric field around it is shown. Now, imagine for a fraction of a second it accelerates. After that, it continues its uniform motion at a higher speed. What we need to understand is the effect of this acceleration on the electric field. The interesting thing is that the information does not travel at an infinite speed. Instead, it travels at the speed of light. Similarly, the information about the sudden variation of velocity of the charge does not get conveyed to the whole electric field region. The field near it knows about it, but the field far away still has no idea that the charge has accelerated and it is still in the old state. Let's separate out these regions with the help of two circles. Since the electric field cannot break, the field between these distances must transition. This transition field is known as a kink. The kink moves or radiates.
I think that the reason why electromagnetic field is asymmetry is because that has to be the relationship of the observer and what's being observed. Because in order to be able to have an experience from, you have to be separated from the thing that you are experiencing. So the relationship between observer and what's being observed is born at the moment of the experience. And it has to be a symmetry because the distance is gonna be equivalent to the separation between the reference frames that are giving rise to the experience, which makes it, and since the space is infinite, the potential is infinite, makes it create a electromagnetic field, which is entangled by the moment that the experience is born, which creates the complexity of everything. And then the distance, the distance of the fluctuation of this field is the law of gravity, but it's not clear how it's born and why it is the way that it is, and not other frequency. I guess this is the problem. Because you can never separate the observer and what's being observed. So you can never know why the law of gravity is the way that it is. And it might be an assumption as well, because you're always assuming after the fact that the experience is already born. So what's most likely happening is that all these possibilities are happening, but the experience is a filter for the possibilities that happens at a certain frequency, which is the law of gravity. And there's an infinite amount of laws of gravity, of different laws of gravity that creates different frequencies. And at the moment that the experience is born, then there is this self-fulfilling prophecy and this entanglement between the observer and what's being observed, which is the frequency of the law of gravity.
It's outwards at the speed of light. To show the kink animation in a clear way, let's move the camera along with the charge. We can say here that the acceleration of
which makes all probability distributions be a self-fulfilling prophecy and an illusion, because there's no way to determine how unlikely events are correlated and if the probability distributions that are observed are real or not, because they're always dependent on the sample size of observation. The frequency of observation is equal to the probability distribution, which is always relative. And depends on the Lorentz transformation. So the reference frames creates probability distributions, which are the geometry of spacetime.
of the charge has caused an electromagnetic disturbance or electromagnetic radiation. Based on this understanding, we will be able to understand the most important experiment in the field of antenna technology, the oscillating electric dipole. The interesting fact about this simple oscillating dipole is that it produces electromagnetic radiation in a perfectly sinusoidal manner. Let's see how it is achieved. Before getting into the electromagnetics, let's understand how velocity and acceleration vary in this simple case. It is clear that at both ends the velocities should be zero, and in the middle, the velocity should be at the maximum. This means that this is a case of continuous acceleration and deceleration. The electric field pattern is drawn here when the charges are far apart and when the velocity is zero. In order to have a better understanding, let's examine one of the electric field lines. Let's observe the electric field line at t by 8. You can see that the electric field line is deformed. The reason for this deformation is simple. This time period is the region with the highest acceleration. As we saw earlier, accelerating or decelerating charges cause kinks in the electric field. In short, the old electric field does not get adjusted to the new field very well. This deformation is continuous since there is continuous acceleration in the charge. When two charges meet at the central point, the deformed line also meets there. After that, it detaches and radiates. This radiation travels at the speed of light. If you plot an electric field intensity variation with respect to length, you can see that the radiation we have produced is perfectly sinusoidal in nature. Please note that this varying electric field will automatically generate a varying magnetic field perpendicular to it. Now, let's have a look at how this applies to an antenna. A time-varying voltage is applied to the metal wire as shown. Due to the effect of the voltage, the electrons will be displaced from right to left and create positive and negative charges. With a continuous variation of voltage, the positive and negative charges will shuttle back and forth in the wire. This simple arrangement is known as a dipole antenna. The dipole antenna produces the same radiation as we saw in the previous section. In this case, the antenna works as a transmitter. The frequency of the transmitted signal will be the same as the frequency of the applied voltage signal. The same antenna can act as a receiver if the operation of the antenna is reversed. When propagating electromagnetic waves strike the antenna, the oscillating fields of waves create positive and negative charges at the ends of the antenna. The varying charge accumulation means a varying voltage signal is produced at the center of the antenna. This voltage signal is the output when the antenna works as a receiver. We can note here that for perfect transmission or reception, the length of the antenna should be half of the wavelength. This is the first antenna design criterion for proper reception or transmission. The second most important design criterion is a term called impedance matching. Perfect impedance matching will make sure that the waves are radiated in the most efficient way. When an alternating current passes through a circuit, it faces opposition from the combined effects of resistance, inductance, and capacitance. This combined effect is known as impedance. According to the maximum power transfer theorem, to transfer the maximum amount of power, the load impedance should match with the source impedance. For further understanding, let's take an example of a circuit containing an alternator as a source and a motor, bulb, etc. as a load. In this setup, to achieve maximum power transfer from alternator to the load, the impedance of the load must match with the impedance of the alternator. A similar impedance balance is required in the case of an antenna system. Since an antenna works on high-frequency signals, the impedance of the transmission lines also becomes important. Hence, to achieve maximum power, the impedance of an antenna should match to the impedance of the source and transmission line as well. If the impedances do not match, some portion of the power would be reflected back to the source instead of radiating outwards from the antenna. A free space has an impedance value of 377 ohms. In a parabolic antenna, a waveguide is used as a transmission line, which has a different impedance value from the free space. That's why a feed horn is also included in a parabolic antenna. This way, the impedance of the waveguide is matched with the impedance of the free space so that the EM waves can be received properly. We hope the concept of such an important engineering phenomenon is clear for you from this video. And please, don't forget to support us. Thank you.
So today we're going to do an electromagnetic calculation problem. We've got Sally Ann and Doc Brown here to help us out if we have any troubles. Here we go. So we're going to try to find the frequency of purple light with a wavelength of 410 nanometers. So the first thing you're going to need to do is write down your variables and your constants to figure out what you're trying to solve for. So the first thing is that we know what lambda is. Lambda is wavelength, and it's 410 nanometers. We also want to solve for frequency, which is nu, and that is our question mark, and that is going to have the units of hertz, or per second is the same thing, or you can write it as second minus 1. All of those are identical to each other. You always have the speed of light constant, which is 3.00 times 10 to the 8th meters per second. Some people do use 2.98, and that's fine also. You can also realize that you have the constant Planck's constant, which is 6.626 times 10 to the negative 34 joules times second. We also could try to solve for energy, but that's not in this problem at this point. If we did, it would have the unit of joules. Over here, what I'm going to do is write down your equations that you can use to solve for wavelength, frequency, and speed of light and energy for any type of electromagnetic radiation moving at the speed of light. So we've got speed of light equals lambda times nu, which is wavelength and frequency. You've got another one where energy is equal to Planck's constant times frequency. And the last one is putting those two equations together, which is Planck's constant times the speed of light divided by wavelength.
Hey everyone, Path here, and in this video I want to talk about something that allows physicists to look at electric and magnetic fields from a slightly different perspective than usual. We'll specifically be focusing on electric fields in this video. We'll be looking at some of the mathematics that allows us to connect electric fields with this new perspective, but as always we'll be keeping the maths as simple as possible. So if you enjoyed this video, then please do hit the thumbs up button and subscribe for more fun physics content. Let's get into it. Now, in a recent video on my channel, I talked about magnetic fields, a related quantity to magnetic fields known as the magnetic vector potential, and how quantum mechanics told us that we probably don't know as much about magnetic fields as we thought we did. And in this video I want to give some more context around this second way of viewing electromagnetic fields. Specifically, I'm talking about potentials, and we'll get to see just why these potentials are so useful. So let's start with electric fields then. The first thing that we need to know is that they describe how electrically charged particles or objects interact with each other. Positive charges are said to be the source of electric fields, and negative charges are said to be the sink of electric fields. The lines we see drawn here in purple are known as electric field lines, and they tell us something about what would happen if we placed another small positively charged particle in this region of space. It would be pushed away from the large positive charge following the direction of the electric field line, and it would also be attracted toward the large negative charge. This makes sense, right? Because like charges repel each other and unlike charges attract. Now, another important point worth knowing is that electric fields are vector fields. This means we can assign a vector to every point in the region of space that we're studying. And the direction of a particular vector tells us the direction of the electric field, or in other words, the direction of the force experienced by a small positively charged particle, and the magnitude or size of this vector tells us something about the size or the strength of the force. Now, because electric fields are vector fields, we can study them using a branch of mathematics known as vector calculus. Because it turns out that there are certain mathematical identities, things that are true generally in mathematics, that apply to lots of different kinds of vectors, including our vector field, that we can essentially steal from mathematics and apply to our electric fields. And we can take these mathematical fields and combine them with the study of electromagnetism. That's the study of electric and magnetic fields. When we do so, we get some rather interesting results. An important thing for me to mention here, as I have done in many of my videos by this point, we'll be seeing a lot of this downward pointing triangle here. This is known as nabla or del, and I've made a full video about it, so check it out up here if you haven't seen it already. All we need to know for now, though, is that there are three important operators that we can use when studying our vector fields. The first of these operators is known as the gradient operator. This essentially takes what's known as a scalar field, a region of space in which we can assign a number to every single point, and it finds, for every single point, the direction in which the scalar field increases the fastest. In other words, we start with a scalar field, whatever the scalar field may be, we find the gradient of it, which looks like this written mathematically, and we end up with a vector field, where each of these vectors tells us the direction and size of fastest increase of our original scalar field. The second operator is known as divergence, which is written sort of as a dot product between the nabla operator and any vector field that we happen to be studying. Again, this is a bit abstract, but all we need to know is that divergence is written mathematically like this. And the third interesting operator is known as curl. It's written like a cross product between nabla and the vector field we happen to be studying. Yet more abstraction, but we'll see why this is important in just a second. Essentially though, these operators just give us some different kinds of information about the original field that we applied them to, whether that's the original scalar field or a vector field. And I'm bringing these up because there's a mathematical identity, like I mentioned earlier, an identity that holds true for many different kinds of vectors, which we'll be looking at here. The identity in question looks something like this. What it tells us is that the curl of the gradient of some scalar is always equal to 0. And for our purposes, the scalars that we're dealing with behave like the scalar fields that we're
Because
looking
it's
at before,
symmetry.
and the vectors that we'll be dealing with look like the vector fields that we've already actually mentioned. But so for our purposes, the curl of the gradient of a scalar field is always 0. Why is this useful? Well, it's because we can take this generic mathematical identity and combine it with something specific from the study of electromagnetism. Specifically, this equation here, commonly known as one of Maxwell's equations. Now, I've covered the details of this equation in a separate video, so check it out up here if you haven't seen it already. But basically what we see here is that the curl of any electric field in a given region of space E is equal to minus the rate of change of any magnetic field in that same region of space, B. In other words, the curl of an electric field is related to how quickly a magnetic field in a given region of space changes over time. Now, to keep things simple, we're going to assume that the magnetic field in the region of space that we want to study is constant. In other words, it might not even exist, or if a magnetic field does exist, it's not changing over time. What this tells us is that this term, dB by dt, must be equal to 0, since the magnetic field is not changing, so the rate of change is...
I think the scope of observation is the right.
is 0. And hence for this scenario, we can now see a similarity between the equation that we're working with from electromagnetism and the original general mathematical identity that we saw earlier. Again, it's important to note that this only applies when there is no changing magnetic field. There is slightly more complicated mathematics that deals with when the magnetic field is changing, but we won't look at that here. All we're going to do though is to spot the similarity between these two equations. We're going to see that the electric field in this region of space that we happen to be studying could be described as the gradient of some scalar field. And so that's a definition that we're going to create now. The electric field is defined as the gradient of some scalar field. And this scalar field is going to be known as the electric potential. And for a couple of different reasons, we're actually going to stick a negative sign in this definition as well, but one really convenient or intuitive way to see this is to recall that the gradient function points in the direction in which the scalar field is increasing the fastest, but for convenience's sake, we want it to point in the opposite direction, the direction in which it decreases the fastest. Why do we want it to point in the direction in which it decreases fastest? Well, to answer that question, I'll just quickly mention here that if you've ever studied electric circuits, you might be familiar with the term potential difference. Sometimes it's called voltage, just to keep things simple, and it's literally a measure of the difference in the value of the potential field at 2 points in a circuit. Positive charges tend to move from areas of higher potential to those of lower potential when moving around a circuit. So the term potential difference is not just a random name for a thing in electric circuits. It's literally the difference between the potential values at 2 points in the circuit. And these potential values directly relate back to the electric field, which is what causes our charged particles to move in the first place. Now let's go back to looking at a generic electric potential field. Here's an interesting fact. The actual value of the potential at any point in this region of space doesn't actually matter, and it's not uniquely defined. What I mean by this is that there's no specific set value for electric potential at any point in this region of space. All that matters is the difference between potential values at 2 points in this region of space, any 2 points. And so a really convenient way to see this is that our potential field could look like this, meaning that the potential difference between, for example, these 2 points is going to be 100 volts. But equally, we could choose to say that our potential field looks like this instead. And so the potential difference between the same 2 points is still 100 volts. And you'll notice that the potential difference between any 2 points is still preserved, but the actual values of the potential at any point do not matter. This is very similar to the following scenario. Let's imagine we want to climb a mountain. We can choose what we define as being a height of 0 meters. Most commonly we do this by defining sea level as a height of 0 meters. And therefore, maybe we calculate that the height of the peak of the mountain is 1,000 meters. But maybe a goat living halfway up this mountain decides that 0 meters should be the height of its favorite patch of grass. This would mean that sea level is now at a height of negative 500 meters in this...
Now, gravity is the difference potential that makes up the electromagnetic field. So what happens when you have infinite gravity? You have an infinitely condensed electromagnetic field, which means that space-time is flat because there's no difference in observation between points. There is no points. Maybe that's why black holes radiate. because once that happens, the natural state is for observation to exist. So it's like an infinite momentum. That's why it creates fractals, because every reference frame of subjectivity that creates the electromagnetic field is a self-fulfilling prophecy in that way that follows the law of gravity. But that still doesn't answer why the gravity is the way that it is, not some other relationship. Maybe there is no answer to that because it always comes after the fact. When you get to an infinite loop of the question of where the Big Bang comes from, then you go to another Big Bang and it goes on forever. So events are only existing relationship to other events. And the momentum of infinity is the law of gravity, but there is no way to find a cause to that because it always existed. So there is no first point from which the momentum started.
new coordinate system, and the peak of the mountain is at a height of plus 500 meters. This is also a valid measurement system because the difference in height between the peak and sea level is still 1000 meters. The most important thing we're learning here though is that we're working with a rather clever goat. So coming back to our potential fields then, we can choose what point in our potential field we want to set as being at zero potential. Now when we study electric circuits, we commonly choose the wire that is grounded or connected to earth.
Maybe the answer is all the points always started, and then the experience is the definition of one of the points. So momentum is created moment by moment by the experience.
To be at 0 volts potential. This is just a convenience thing, it doesn't have to be this way, and it's similar to how we choose sea level to commonly be our height of 0 meters. And with all of that being said, I'm going to finish up here. Thank you so much for watching. If you enjoyed this video, please do hit the thumbs up button and subscribe for more fun physics content. Hit that bell button if you'd like to be notified when I upload, and please do check out
Yeah, but then that wouldn't answer when the experience, what determines when the experience begins and when it ends. The transition between different gravities.
Particles with opposite charges attract one another. We can view this by saying that the positive particles that are far away from the negative particle have a higher potential energy, just as in the case of gravitational potential energy.
Because the same thing.
Particles with the same charge repel one another. We again can view this as a case of potential energy. Although gravitational fields affect all objects in the same way, electric fields have an opposite effect on positive particles than they do on negative particles. From a negative particle's point of view, the potential energy throughout space is flipped upside down, as compared to a positive particle's point of view. Every charged particle contributes to shaping the electric potential energy at each point in space. The effect of each particle adds together. Suppose we have charged particles that are trapped inside a container. The charged particles will move to the edges of the container, causing the electric potential energy to be the same everywhere inside the container. If a container with charged particles experiences an external electric field, the charged particles inside the container will react by again moving in such a way so as to cause the electric potential energy to be the same everywhere inside the container. The charged particles inside the container will react by again moving in such a way so as to cause the electric potential energy to be the same everywhere inside the container. In a metal conductor, the positively charged particles are always fixed at one spot and unable to move, but the negatively charged particles are free to wander around. When the metal conductor experiences an external electric field, one side of the metal will end up having more negative particles than positive particles and develop a net negative charge. The other side of the metal will end up having more positive particles than negative particles and develop a net positive charge. Therefore, the effect is the same as in the example of charged particles inside a container. The electric potential energy is the same everywhere in the metal. In an electric circuit, the negatively charged particles flow through metal wires. Metal wires that are directly connected to each other with metal connections are all at the same electric potential. The difference between the electric potential energy of 2 points of a circuit is what we call the voltage. When a switch closes, it causes the two different parts of a circuit that it connects to be at the same potential energy. The number of charged particles that pass by each second is what we refer to as the current. When electricity was first discovered, it was not known that it is the negatively charged particles that move through wires, and it was incorrectly assumed that it's the positive particles that are moving in the opposite direction. The convention for how we describe the electric current's direction was never updated, and we therefore still refer to this situation as if it is the positive particles that are flowing in the opposite direction. Much more detailed information about voltage, current, and electric circuits is available in the other videos on this channel.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be discussing voltage. We'll learn what is voltage and potential difference, how to measure voltage, the difference between direct and alternating voltage as well as current, and finally, we'll briefly look at why and how voltages vary around the world. In our last video, we learned that electricity is the flow of free electrons between atoms. Voltage is what pushes the free electrons around a circuit. Without voltage, the free electrons will move around between atoms, but they move around randomly, so they aren't much use to us. It's only when we apply a voltage to a circuit that the free electrons will all move in the same direction, causing current. It's easy to imagine voltage like pressure in a water pipe. If we have a water tank completely filled with water, then the mass of all that water is going to cause a huge amount of pressure at the end of the pipe. If we have a water tank that's only partly filled, then there will be much less pressure in the pipe. If we open the valve to let the water flow, then more water will flow at a faster rate from the high pressure tank compared to the low pressure tank. The same with electricity. The more voltage we have, then the more current can flow. Voltage can exist without current. For example, we can measure the pressure in the pipe with the valve shut with no water flowing, and from this we can tell that the pipe is pressurized. What we're really measuring is the pressure difference between what's inside the pipe compared to the pressure outside. The same thing if we have a battery connected to a circuit with an open switch. The voltage is still present, we can measure that, and as soon as the switch closes, it's going to push the free electrons around the circuit. We sometimes hear voltage referred to as potential difference. This really means how much work can potentially be done by a circuit. Coming back to our water analogy, if we have two lakes at the same level, then there is no potential to do work because the water isn't flowing. But if we raise one lake higher than the other, then this higher lake now has the potential to flow down to the second one. And if we give it a path, then it will flow. If we place a turbine in its path, then we can use its energy to power a light or even an entire town. Back to the electrical circuit, this battery has a potential difference of 1.5 volts between its negative and positive terminal. If we connect a piece of wire to both terminals of a battery, then the pressure of the battery will force the electrons to flow all in the same direction along the same path. We can then place electrical components in the path of these electrons to do work for us. For example, if we place a lamp into the circuit, then this will light up as the electrons flow through it. If we then added another battery to the circuit in series, then the electrons will effectively be boosted by the second battery because they can only flow along this path and there is more energy being added. This will combine the voltages so we get 3 volts. More volts equals more pressure, which means more pushing force. That will mean more electrons will flow and the lamp will glow brighter. However, if we were to move the battery and connect it in parallel, then the path of the electrons splits. Some will flow to the first battery and some will flow to the second battery. Therefore, the batteries will both provide the same amount of energy, so the voltage isn't combined. The voltage isn't boosted and we only get 1.5 volts. So the workload is split by the batteries and the lamp will be powered for longer, but it will be dimmer. We've covered this in much more detail within our electrical circuit series. Do check that out, links are in the video description below. We measure the potential difference of voltage with the units of volts, and we use the symbol of a capital V to show this. If you look on your electrical appliances, you will see a number next to a capital V indicating how many volts the product is designed for. In this example, the manufacturers of this USB hard drive are telling us that the device needs to be connected to a 5-volt DC or direct current supply, and it needs 1 amp of current for the device to work. The term volt comes from an Italian physicist named Alessandro Volta, who invented the voltaic pile, which was the first electrical battery that could provide an electrical current in a steady rate in a circuit. Voltage and volts are different. Remember, voltage is the pressure, and volts is just the units we use to measure it in. The same as we know the pipe has pressure, but we use units to measure this pressure, such as bar, PSI, KPA, etc. As we saw earlier, we can measure volts with a voltmeter. This can be separate or part of a multimeter. If you don't have a multimeter yet, you can pick one of these up really cheaply. I highly encourage you to have one in your toolkit. I will leave a link in the video description down below for where to get one for a good price. To measure voltage, we have to connect to the circuit in parallel across the 2 points we would like to know the voltage or potential difference for. So for a single battery in a circuit, then we measure 1.5 volts across the battery, and we also measure 1.5 volts across the lamp. The battery is providing 1.5 volts to the lamp, and the lamp uses 1.5 volts to produce light and heat. In a 2-lamp series circuit, we measure 1.5 volts across the battery, 1.5 volts across the 2 lamps combined, but 0.75 volts across the lamps individually. The voltage or potential has been shared between the lamps to both provide light and heat. The lamps are dimmer because the voltage has been shared or divided. Again, we'll cover this in more detail in our electrical circuits tutorials. So we saw earlier that voltage and volts are different. Voltage is pressure and volts is the unit of measurement. So what does 1 volt mean? 1 volt is required to drive 1 coulomb, or approximately 6,242 quadrillion electrons, through a resistance of 1 ohm in 1 second. That's still a little confusing, so another way to explain this is that to power this 1.5 watt lamp with a 1.5 volt battery would require 1 coulomb, or 6,242 quadrillion electrons, to flow from the battery and through the lamp every second for it to stay on. To power this 0.3 watt lamp with a 1.5 volt battery would require 0.2 coulombs, or approximately 1,872 quadrillion 600 trillion electrons, to flow from the battery and through the lamp every second for it to stay on. If we try to use a lower voltage, the lamp would turn on, but it decreases in brightness as the voltage decreases. That's because there is less pressure to force electrons through it. Less electrons flowing, less light that can be produced. The lamps are only rated for a certain voltage and current. If we use a higher voltage, then the lamp will become brighter because more electrons are flowing through it. But if we add too much voltage and current, then the lamp will blow because too many electrons try to pass through at once. If we look at some typical batteries, we can see that this AA battery has a voltage of 1.5 volts, and this one has a voltage of 9 volts. These are sources of direct voltage, meaning the pressure it provides moves the electrons in a constant current in one direction, much like the flow of water down a river. We cover this in our last video on electricity basics, so do check that out if you haven't already. Links are in the video description below. Direct voltage is usually represented with a capital V with some dots above this and a small horizontal line. You can see an example of this on the multimeter for the setting we would need in order to measure the voltage in a DC supply. If we plotted this voltage against time, it would produce a straight line because it is constant, it is direct in one direction. The voltage in our wall sockets is alternating voltage. This is a different type of electricity. In this type, the electrons alternate between flowing forwards and backwards because the polarity of the circuit is changing, much like the tide of the sea. If we plotted this voltage against time, we would get a sine wave as it moves forwards and rises to its maximum and then starts to decline. It passes through 0, and now the current is flowing backwards, but it then hits its minimum and reverses direction again. This is usually represented with a capital V with a wave line above it. You can see that on the multimeter here, also for measuring AC voltage. The voltage at these sockets varies depending on where in the world we are. The majority of the world uses 220 to 240 volts, but North, Central and some of South America, as well as a few countries scattered across the planet, will use 110 to 127 volts. We can measure the voltage at our sockets and see that it actually changes slightly throughout the day as the demand on the electricity network varies. And we can do that using one of these cheap energy meters. Again, links in the video description down below. If you want one of these, you can pick them up fairly cheaply and they're a great device for your toolbox. The reason for different voltages around the world goes all the way back to the beginning when electricity first started being distributed. At first, there was no standardization, so each distribution network had its own voltage and frequency for whatever their engineers felt was best. Eventually, over time, some companies grew and dominated the market, and so voltage and frequency standardized as their products and services expanded. Governments also had to step in and pass laws and regulations to help standardize their countries so that people could buy products easily, but also trade products with other countries. This is still a problem to this day, but it's pretty much too late to fix as everyone is now so reliant on their electrical devices, and we would need to replace or modify them all to solve the problem. For example, if we take a hairdryer from the US, which is rated at 110 volts, and we plug it into a wall socket in Europe which has 220 volts, the hairdryer will burn out at full power because there is just simply too much voltage or too much pressure and the device just can't cope. If we took a hairdryer from Europe and plugged it into a US socket, it probably won't turn on, but if it does, it's not going to be very strong, it's going to be pretty weak because there just isn't enough pressure for it to function. Some products can be used in different voltages though. You need to check the manufacturer's labels on the product to first see if the product has been designed to cope with different voltages. For example, this laptop charger shows that it can be used on voltages between 100 and 240 volts, whereas this charger is only rated for 220 volts or 240 volts. Okay guys, that's it for this video, but if you want to continue your learning with your electrical engineering, then check out these videos here and I'll catch you there for the next lesson. Leave your questions in the comment section down below and don't forget to follow us on Facebook, Instagram, Twitter, as well as theengineeringmindset.com. Once again, thanks for watching.
Gravity and magnetism. And we'll cover gravity first, right? It's a force, and Isaac Newton related the gravitational force to the product of two masses. And there you see the moon, mass 1, and the Earth, mass 2. And by the way, all the calculations in this presentation can be found in the paper. URL is there, but I'm also going to put it in the description so you can click on it for easy access. So gravity is a force. Right? It's a force that can attract objects of any mass. Right? The moon was shown on the earlier page. People, we're standing on the Earth right now because of gravity. Even to light things like feathers. And at least in a vacuum, all of those objects are going to fall at a constant rate. At Earth's surface, that's 9.81 meters per second squared. But now imagine
There's no push
two
and pull.
people, right?
Push can only exist in relationship to pull. Pull can only exist in relationship to push.
Gravity and magnetism. And we'll cover gravity first, right? It's a force, and Isaac Newton related the gravitational force to the product of two masses. And there you see the moon, mass 1, and the Earth, mass 2. And by the way, all the calculations in this presentation can be found in the paper. URL is there, but I'm also going to put it in the description so you can click on it for easy access. So gravity is a force. Right? It's a force that can attract objects of any mass. Right? The moon was shown on the earlier page. People, we're standing on the Earth right now because of gravity. Even to light things like feathers. And at least in a vacuum, all of those objects are going to fall at a constant rate. At Earth's surface, that's 9.81 meters per second squared. But now imagine two people, right? They don't experience a detectable gravitational force, right? And that's because the mass of a single person is too small for gravity to be detected. The key word there is detected. I'll go over that in a little bit. Now, the average person has 10 to the 27th power number of atoms. That's a lot of atoms, right? You can see an atom there, a single atom on the far left. But that pales by comparison to the Earth, which has 10 to the 50th power of atoms. So a heck of a lot of atoms. Magnetism, right? That's also a force. Now, within the Earth contains an iron core, and it's responsible for its magnetic field. And what's a force? A force has the ability to move objects. And so think about the compass, and that force causes the needle of a compass to align with a magnetic field and point north. And the Earth has an iron core, and you can think about an iron bar magnet, but there's other elements that are also magnetic, and they're magnetic when particles and their spin align. And so here's a bar magnet with a north and south pole, and you can see the field lines that are drawn. But all that originates because of this, right? A single particle like the electron has a magnetic moment due to spin. So you can see the same magnetic field lines coming from a single particle. You line those, you get magnets, such as the bar magnet. You line it in the core of the Earth, you get a magnetic field in a planet. All right, let's break this down and explain gravity first. All right, to explain it, let's imagine an incredibly small particle, right, radius of Planck length, and that's very small. You can see the number down there at the very bottom. And in fact, all of the constant you're going to see here will appear at the bottom with their value and units. Okay, so let's do this. Let's imagine an in wave, right? These are electric waves, longitudinal waves to be specific, converging on that particle you see on the far left. Now, imagine two out waves, right? One is longitudinal, spherical, longitudinal waves, and the other causes a motion, in this case, the spin of that particle, and a second out wave forms, which is, depending on your view, it's transverse. And longitudinal and transverse will be described in just a second. So one in wave, two different types of out waves. And these values here are going to be important for the rest of this presentation. Right, it's conservation of energy, and by the way, these are wave amplitude, and energy is proportional to the wave amplitude squared. So energy is conserved, and it's going to be Planck charge coming in, and then what will be shown to be the elementary charge is Planck charge and the square root of the fine structure constant, and then the other is the Planck charge divided by the square root of the fine structure constant. This will be explained in a second, but remember these values, it's going to be key. Now, the next few slides are actually taken from a separate paper and a video on that paper, but it's important to just do a quick recap of this. So particles can be formed from charge, or they're standing longitudinal waves, right? It's an in wave and an out wave creates a standing wave, and that becomes the particle. And beyond that, it's traveling waves. And for more information, go to that paper. I'm just doing the quick recap. Now here is the icons that are going to be used instead. It's really hard to show spherical waves, so we're going to use those arrows as the longitudinal wave, which is in the vibration is in the direction of propagation. That's a longitudinal wave, and that's going to be the electric wave. From the poles now is going to be a transverse wave, which is vibration at right angles to the direction of wave propagation, and that's going to have a separate icon there. That red spinning line is going to be the magnetic wave. Okay. Now, the electron's mass can be derived as following, and so can the electron's energy, and the only difference in that equation is that c squared, see a little c there. So the difference between mass and energy is wave speed, and what is a particle? Well, a particle can be measured as either mass or energy, typically because they are stored energy. And what's a standing wave? A standing wave has energy, but it's no net propagation of energy. It's stored energy. So everything that we define within that radius, RE, which is the electron's classical radius, is stored energy and becomes a particle. But energy continues to flow beyond there. We just don't call it energy because at that point, traveling waves have the ability to force another particle into motion. What do we call that? We call it a force. And a force is just energy divided by a distance. And so that same equation you saw for energy on the previous page now has r squared in the denominator instead of r, right? That's energy divided by distance. That is the electric force equation. You might be more familiar with it as Coulomb's law, F equals kQq over r squared, but that is the exact same thing. The magnetic constant is used here because of the previous page, as you can see, to separate energy and mass. But to the left of those parentheses, magnetic constant and c squared divided by 4 pi is the Coulomb constant. And then what you see there is as the elementary charge, it's just for two particles. But of course, Q is the number of particles times the elementary charge. So that is Coulomb's law, just shown in a different way. Okay, that's a quick recap. So let's do this. In waves are reflected as longitudinal out waves. And if you want a better visual of this, think about sound waves, for example. Those are longitudinal waves bouncing off a balloon. Most of that energy is reflected, but what if it causes a slight turn of that balloon? Then you would have a second waveform. But that slight difference of in-wave and out-wave energy results in this, right? A net longitudinal in-wave. And due to the conservation of energy, that energy equals that magnetic spin coming out. Okay, all this will make sense when we put equations to it and can prove it. So let's do this first. Let's calculate that longitudinal energy. It's really small by comparison of what is lost, and it occurs at the core at Planck length and extends out to the particle standing wave radius, which is the electron's classical radius. Now you square that ratio and apply the fine structure constant, and you get what's called the electron gravitational coupling constant to the right. Now that energy loss, what you're going to see in magnetism is really small, right? What's energy? mc squared. So we're going to take the electron's mass, c squared, and then apply that coupling constant. Gravity is measured as a force. We're going to take that energy divided by distance, and that distance is going to be applied at the electron's radius. And this equation at the bottom right is going to be used later. So remember that. I'll show the equation later, but just remember this one. But first, that energy loss is really small. And remember that longitudinal waves are still being reflected. The vast majority of them are being reflected, and that is the electric force. So gravity pales by comparison to the electric force, and it's not detected for two particles. But you can take the force of gravity and divide it by the force of electricity, and this is where we start to see the gravitational constant g and Coulomb's constant k. You don't see the r squared in the equation there in the bottom left because they cancel out, but that's essentially Coulomb's law and Newton's law. Notice that it's the exact same value as electron gravitational coupling constant. That's no coincidence. These forces are a result of that ratio. So gravity pales by comparison to the electric force. But let's just say that electric force is neutralized. Right? So in the absence of any electric force, what would happen? If there's slight net energy of spherical longitudinal end waves that creates pressure on a particle. But now when you put two or more of those together, you get a shading effect of pressure. Same thing as the radiation pressure, which is witnessed. Right? And what does that do? It forces two particles together. So gravity is not a pull force, it's a push force. But the electric force does exist, right? So gravity remains undetected for two particles. And remember that ratio, the ratio of the gravitational force to electron force, it would take 10 to the 43 power number of electrons with gravitational force equal just the electric force of two electrons, a lot of electrons. We're going to be showing atoms later, so it's worth noting that it takes 10 to the 37th power of protons equal that same electric force of two electrons. You do that by taking the proton to electron mass ratio and squaring it. Anyway, what has that number of protons and electrons in atoms? Well, a large body like Earth. Right? That explains why we see it in large bodies. Okay, from earlier, the force of gravity for a single electron mass, remember this one? At its radius was that. All right, that's a force equation. Now, Newton established the force of gravity as a product of two masses, and he had to insert the proportionality constant, gravitational constant, known as g. So, for example, two electrons, you see g in the mass of two electrons and separated by its radius there. Well, that's a problem for force equation, which in units has one mass. And so you have to account for that in the proportionality constant g. So how do you solve for that? Right, you take that force equation in the top left, you bring the mass down to the denominator and the radius up to the numerator. And now the masses cancel out in terms of units. And what do you get? You get the derivation now of the gravitational constant in both value and also units, and with an explanation now for the constant g. Oh, but wait, there's a lot more. Because we're going to get to magnetism now and explain how magnetism is related to gravity. So let's do this. Let's consider a particle that spins in one of two directions, counterclockwise or clockwise, and it creates two transverse waves at its poles. Now, the magnetic moment for the electron is actually a strange one in terms of units. It's not energy or forces, which would make life a lot easier to be able to explain everything. Its units is something called joules per Tesla. But everything else so far has been measuring coulombs, which is the unit for charge, as wave amplitudes. And wave amplitude is distance, right? So meters and SI units. When you do that conversion, you can see joules per Tesla there at the bottom left. It becomes a volumetric flow rate, meters cubed per second, which is makes it a lot easier, makes a lot more sense to explain magnetism now. It's flowing out of the electron at that rate. And what is the electron's magnetic moment? It's known as the Bohr magneton. So let's derive that now, right, with a wave speed of c, right? That's the speed of light. All the electromagnetic waves travel at that speed. Measured flowing out of the electron's radius at that amplitude earlier. Remember, the amplitude is Planck charge divided by the square root of the fine structure constant. Now we're measuring it at one pole, right? There's 2 poles, so we take half of that. And what do you get when you put all that together? You get the volumetric flow rate in terms of units that I explained, but you also get the value of the Bohr magneton. It's a flow rate. Now, because of the Planck length relationship, the electron's gravitational coupling constant, see that flashing arrow there, it can also be used. You take the Planck charge and the Planck length and the speed of light, divide that by the electron's square root, at least the electron's gravitational coupling constant. What do you get? You get the Bohr magneton. So that's one of the first equations now that directly relates gravity and magnetism. All right, there's more. So an electron paired with a proton creates this simplest atom, which is hydrogen. And the electron is also known to orbit. The most probable orbital distance, at least, is known as the Bohr radius. And there it is. Now, the flow rate has to be described flowing through something. So we're going to take a volume here. Right? In between the electron and the proton, we're going to take a cross-sectional area of the electron, pi r e squared, and we're going to multiply that by the length or radius, and we get a cylindrical volume. So let's put that cylinder here as the energy between the electron and the proton. And then now let's take the Bohr magneton, square it for flow rate coming in and out of the electron, flowing through that volume with a linear density of magnetic constant. If you do those units now, you get units of energy. So we made an energy equation. And if you look at that value, that energy, that magnetic energy between the electron and proton is exactly equal to the rest energy of the electron. All right, so now that proton and electron forms hydrogen and other elements form, or atoms neutralizing the electric force. And you put all those together, they make all sorts of different things, including people, but also large bodies like Earth and like the moon and stars like the sun. Right? They contain a significant number of atoms, such that now that same shading effect that was shown for 2 particles actually can be detected. Gravity is the measurable force in a large body, and it's the same shading effect of that individual particles, but it can be detected due to the sheer number of particles in these planets and moons. And magnetic fields may form in large bodies, like the Earth when particles spin a line. That was shown earlier. The iron core creates the magnetic field. But it's the electric fields. What comes into each and every one of these particles is conservation of energy causing them to spin that links gravity to magnetism. And you can even see it at a macro level here. We saw it at the particle level, but you can see at a macro level here that even Earth's magnetic field is intricately linked to its gravitational force. And it's because of every spinning particle on and within the Earth.
Special relativity cannot deal with accelerating objects or accelerating frames, because special relativity only deals with inertial reference frames, and that we need general relativity to deal with acceleration. This is incorrect and is a common misunderstanding. In fact, special relativity can handle accelerating objects and accelerating reference frames just fine. I think now is a good time to explain the differences between special relativity and general relativity, so that we can understand where special relativity ends and where general relativity starts. Special relativity is a theory of relativity that we get when we take the speed of light in a vacuum c to be constant in all inertial reference frames. Special relativity ignores gravity, and special relativity only considers flat space-time. Meanwhile, general relativity is a theory of gravity that we get when we accept the equivalence principle, which says that a local gravitational field is completely equivalent to an accelerating frame. And so general relativity does take gravity into account. General relativity is a theory of curved spacetime and treats gravity as a manifestation of curved spacetime. Now, I realize that a lot of what I just said about the equivalence principle and curved spacetime probably doesn't make much sense right now. We'll be getting to those in future videos. But the point is that the main difference between special relativity and general relativity is that special relativity ignores gravity, whereas general relativity includes gravity. Special relativity cannot deal with gravity, but there's no rule that says special relativity can't deal with acceleration or non-inertial frames. That said, special relativity treats inertial frames and non-inertial frames as fundamentally separate situations. In inertial frames, the laws of physics, ignoring gravity, are all the same, and the speed of light is constant. When viewed from other inertial frames have constant velocity and have straight-line coordinate systems. Meanwhile, non-inertial frames experience extra fictitious forces in addition to the normal laws of physics. These fictitious forces depend on the reference frame, similar to when you get thrown into the back of a car seat when the driver steps on the gas pedal. In non-inertial frames, the speed of light is not constant. Later in this video, we will look at a non-inertial frame where a light beam appears to be frozen in space with zero velocity. When viewed from inertial frames, non-inertial frames have a changing velocity, or acceleration, and have curvilinear coordinate systems. It's important to note that, even though non-inertial frames in special relativity have curved coordinate lines, the spacetime they describe is still flat, like the surface of a table or a flat computer screen. On the left, we have a straight-line coordinate system drawn on a flat surface, and on the right, we have a curvilinear coordinate system drawn on a flat surface. Both coordinate systems describe flat geometry. We won't see truly curved geometry until we get to general relativity. The Relativity 105 videos are all about acceleration in special relativity. In this video, we'll talk about hyperbolic motion, which is what constant acceleration looks like in special relativity. We'll also show how acceleration leads to the creation of a Rindler horizon, which is similar to the event horizon of a black hole. In the next few videos, we'll talk about Rindler coordinates and Bell's spaceship paradox, basis vectors and the Jacobian in curvilinear coordinates, proper time along curves and the twin paradox, the covariant derivative, and finally geodesic curves, which are the curves that inertial frames travel along. Let's start by talking about constant acceleration in Newtonian physics. You probably know that an object traveling at constant acceleration in Newtonian physics traces out the curve of a parabola, as seen by falling objects on Earth in everyday life. If we draw a parabola on a space-time diagram with time on the vertical axis, we immediately see a problem. Recall that a beam of light travels at a 45-degree angle on a space-time diagram. We can see that, in this portion of the parabola, the object is traveling faster than the speed of light, which we know is impossible from Relativity 104 Part D. So we know that an object undergoing constant acceleration in special relativity cannot trace out a parabola curve, because that would mean the object would eventually travel faster than light. Instead, we'd expect an accelerating object in special relativity to trace out a curve more like this, something that goes faster and faster but never actually reaches the speed of light. This curve of constant acceleration in special relativity is called a hyperbola, where the time and space coordinates are given by hyperbolic sine and hyperbolic cosine of the hyperbolic angle. See Relativity 104 Part E if you want to review hyperbolic geometry. To prove that constant acceleration in special relativity gives us a hyperbolic curve, we're going to follow 3 steps. Number 1, we're going to prove that the 4 velocity and 4 acceleration vectors of an object are always orthogonal. Number 2, we're going to define exactly what we mean by constant acceleration in special relativity. And number 3, we're going to derive the equations of motion for the spacetime world line of an object traveling with constant acceleration. The first step is to prove that an object's 4 velocity vector is always Minkowski orthogonal to its 4 acceleration vector. In other words, u dot a equals 0. Remember, the ordinary Euclidean version of orthogonal means that 2 vectors meet at a right angle. But the Minkowski version of orthogonal means that 2 vectors meet at equal angles with a beam of light in a spacetime diagram. The proof is easy. We just take the derivative of u dot u and use product rule over the dot product. Since the order of the dot product inputs doesn't matter, this is just 2 of the same term added together. The derivative of 4 velocity with respect to proper time, du by d tau, is just the 4 acceleration vector a. Now, we know that u dot u is always c squared, which is constant, so its derivative is 0. And dividing both sides by 2, we see that u dot a equals 0 always. We can think of this as being like a law of physics in special relativity. It makes logical sense that a is always orthogonal to u. Since the Minkowski length of u is constant, acceleration cannot make it longer or shorter. Acceleration can only change its direction. This means that all acceleration must be orthogonal to u, because acceleration can never be parallel to it, because that would make u longer or shorter. So we've proven that u dot a equals 0 always. The next step is to define what we mean by constant acceleration. In normal Newtonian physics, we could just say that constant acceleration means that the components of the 3 acceleration vector, ax, ay, az, are constant. But because time and space are relative in special relativity, Newtonian acceleration is also relative, and we need a new way of defining constant acceleration. Instead, we're going to define what is called the proper acceleration. Recall, the proper time for a moving observer is the amount of time measured by a clock that the observer is carrying with them. Similarly, proper acceleration is the acceleration measured by an observer using an accelerometer that they are carrying with them. You're probably familiar with the feeling of getting thrown backward inside an accelerating car, or feeling heavier when an elevator accelerates upward. It turns out that it's possible to build an accelerometer, which is a mechanism that measures accelerations like this. Most modern smartphones have accelerometers inside of them, and you can download an accelerometer app to measure your proper acceleration in different directions. In this video, we're going to look at the case of constant proper acceleration, which refers to an accelerating observer that always measures a constant number on an accelerometer that they are carrying with them. Let's say that the physicist Wolfgang Rindler is traveling along a world line with constant proper acceleration in the positive x direction. Let's try to understand his acceleration from his own reference frame and also from the frame of Einstein, who is standing still in a stationary frame nearby. We know that a Lorentz transformation can always change coordinates from an inertial frame to any other inertial frame, which has a straight world line. But a Lorentz transformation cannot change coordinates from an inertial frame to a non-inertial frame, because non-inertial frames have curved world lines. However, we can always find a Lorentz transformation that brings us to an inertial frame for one specific point on a curved world line. For example, the inertial world line of this rocket is tangent to Rindler's world line at exactly this one event point. This means at this event point, both Rindler and the rocket have the same 4 position and the same 4 velocity. So for this one instant in time, the rocket and Rindler have the same inertial reference frame, given by a spacetime basis et tilde and ex tilde, and we can find a Lorentz transformation from Einstein's stationary frame to this momentary inertial frame at this exact event point. This other rocket's inertial world line is tangent to Rindler's world line at this point, so this would be their common inertial frame at this instant. And for this other inertial world line, this would be Rindler's common inertial frame at this instant. So a curved world line in spacetime is like a series of instantaneous inertial frames, where every event point along the curved world line has its own inertial spacetime basis, where the time basis vector is tangent to the world line curve and the position basis vector is orthogonal to it. An instantaneous inertial frame is also called a momentary inertial frame, or a momentarily co-moving reference frame, MCRF. So while we can't find a Lorentz transformation that works for Rindler's entire world line, we can find a Lorentz transformation that brings us to an instantaneous inertial frame at any given point along his curved world line. Also, by definition, the 4 velocity vector is also tangent to a curved world line at any given point, because it must match the direction of the world line of an inertial observer. And as we've shown, the 4 acceleration vector is always orthogonal to the 4 velocity. So this means that in an instantaneous inertial frame, the 4 velocity u is always parallel to the time basis vector, because they are both tangent to the curved world line. This means that the 4 velocity vector always has 0 space components from Rindler's point of view. This basically means that the observer in this frame thinks they are always stationary in space. And the 4 acceleration a is always orthogonal to the 4 velocity. So this means that in the instantaneous inertial frame, the 4 acceleration is always purely in a spatial direction, with a 0 time component. So when we say Rindler has constant proper acceleration, this means that the components of Rindler's 4 acceleration vector are always constant and point in the space direction only for his instantaneous inertial frame. But the nearby stationary observer Einstein will see Rindler's 4 acceleration vector have a different mix of time and space components depending on when Einstein measures it. If we assume Rindler's acceleration is only in the x direction, then he would calculate his 4 acceleration a to be alpha times ex tilde, where alpha is the size of his proper acceleration. This means that a dot a equals negative alpha squared, where the negative sign means that a is a space-like vector. Even if the stationary observer Einstein sees the components of Rindler's 4 acceleration vector to be constantly changing, he will still agree that a dot a equals negative alpha squared for Rindler's 4 acceleration vector, because the dot product of 4 vectors is invariant and agreed upon by all observers, regardless of the reference frame. So our condition for an object having constant proper acceleration alpha in their own frame is that their 4 acceleration vector dotted with itself gives the constant value of negative alpha squared. This is true assuming that the acceleration is only in the x direction. Finally, the last step is to derive the equation of a world line traveling with constant proper acceleration. We are going to analyze Rindler's accelerating motion from Einstein's stationary inertial frame, with basis et and ex. We are going to assume that no motion occurs in the y or z directions, so we only need to worry about the x-axis and the time axis. Our goal is to measure the components of the 4 velocity vectors u and the 4 acceleration vectors a along Rindler's world line, measured in Einstein's spacetime basis. We already know that it's always true that the 4 velocity dotted with itself gives c squared. In Einstein's frame, Rindler's 4 velocity dotted with itself equals ut squared minus ux squared. We also showed that it is always true that u dot a equals 0. In Einstein's frame, this means that UT-AT minus UX-AX equals 0. Finally, in the special case of constant proper acceleration, we have a dot a equals negative alpha squared, which is at squared minus ax squared. We'll start with the fact that u and a are orthogonal. UT-AT equals UX-AX. Then we'll square both sides. Now, based on u dot u equals c squared, we can replace ux squared with ut squared minus c squared. And based on a dot a equals negative alpha squared, we can replace ax squared with at squared plus alpha squared. If we distribute this multiplication, we get 4 terms: ut squared at squared minus c squared at squared plus alpha squared ut squared minus c squared alpha squared. Ut squared at squared cancels on both sides, and we can factor out alpha squared from both of these terms. We can move this to the other side and then replace ut squared minus c squared with ux squared. Taking the square root of both sides, we finally get at equals alpha over c times ux. And if we follow this process again from the beginning, but substituting for the time components instead of the x components at the start, we get another similar equation, ax equals alpha over c times ut. Now, it is technically possible that we could get either a plus or a minus sign when we take the square root here, but we're choosing the positive x solution because we want the observer to be accelerating in the positive x direction instead of the negative x direction. Now, since we are observing from an inertial frame, basis vectors are constant everywhere in spacetime, and their derivatives go to 0. This means that we are lucky, and the derivatives of the components of the 4 velocity are exactly equal to the components of the 4 acceleration. So at equals dut by d tau, and ax equals dux by d tau. So we have 2 coupled differential equations. Alpha over c ux equals dut by d tau, and alpha over c ut equals dux by d tau. The first step is to multiply both sides of the second equation by c over alpha. This basically moves the constant from the left side of the equation to the right side and takes the reciprocal. Given this pair of differential equations, we can sub ut from one into the other, and then we get ux times alpha squared over c squared equals the second derivative of ux with respect to tau. If you know about differential equations, you might know that there are exactly 2 kinds of solutions to the problem of a function being proportional to its second derivative. The solutions are e to the alpha over c times tau, or e to the negative alpha over c times tau. You can plug either of these solutions into ux in this differential equation to confirm that they work. In fact, any combination of these solutions added together with constants k1 and k2 also works, and you can plug this into ux to confirm that this is true. Now, differential equations always have multiple possible curves as their solutions, depending on the constants that you choose. In order to get unique constants, we need to choose an initial condition. Let's say that our initial condition is that the x velocity is equal to 0 when tau equals 0. So the 4 velocity vector only points in the time direction at time tau equals 0. So if we take ux and set it to 0 when tau equals 0, we get that k2 equals the negative of k1. And subbing this in, we can factor out k1 from our formula for ux. We can then plug ux into this second differential equation that we had, and we get a formula for ut. And when we take the derivative, we get an extra factor of alpha over c in front, which cancels with c over alpha. Also, the second exponential changes sign because we took the derivative of a negative exponential, so the minus sign comes out in front. So the formulas for ux and ut are the exact same, except for the sign of the second exponential term. Now, we know that ut and ux are not independent of each other, because we know that u.u equals c squared for any 4-velocity vector. This law should apply for all values of tau, so let's plug in tau equals 0 to simplify the formula. We know that when tau equals 0, we said that ux equals 0, because of the initial condition that we chose. And plugging tau equals 0 into the formula for ut, the exponentials to the power 0 just go to 1 plus 1. Taking the square root of both sides and dividing both sides by 2, we get that k1 equals 1/2 c, half the speed of light. We're taking the positive solution to the square root to ensure that our 4-velocity vectors point from the past to the future instead of the future to the past. Now, it turns out that for some variable phi, 1/2 times e to the phi plus e to the negative phi is equal to hyperbolic cosine of phi. And 1/2 times e to the phi minus e to the negative phi is equal to hyperbolic sine of phi. You can pause the video and prove to yourself that the fundamental identity cosh phi squared minus sinh phi squared equals 1 is also true for these exponential formulas. So really, these are just two different representations of cosh and sinh. So really, ut is just c times cosh of alpha over c times tau, and ux is just c times sinh of alpha over c times tau. It's also easy to see that the derivative of cosh phi with respect to phi using the exponential representation is just sinh phi. And the derivative of sinh phi with respect to phi is just cosh phi. Given these formulas for the 4-velocity components, it's easy to check that u.u equals c squared, as expected. Using the time and x components for the 4-velocity, we can immediately get the components of the 4-acceleration by taking their derivative with respect to tau. And we can see that a.a equals negative alpha squared as expected. We can also get the spacetime 4-position components by taking the integrals of the 4-velocity components with respect to tau. And we get integration constants kt and kx added on at the end. These integration constants represent another initial condition, the initial position in spacetime of the accelerating observer. For simplicity, we'll set them to 0. This means that our initial time position is 0, and our initial space position is c squared over alpha. We can also see that, in this special case, the observer has a constant spacetime interval, s.s, of negative the square of c squared over alpha. The proper time tau is the time that Rindler measures on his own wristwatch as he travels along his world line from bottom to top. With negative tau being on the bottom half, tau equals 0 is the point where he crosses the x-axis, and tau greater than 0 is the upper half of the world line. If we draw the initial conditions as vectors, the 4-position s at tau equals 0 is c squared over alpha on the x-axis, and the initial 4-velocity at tau equals 0 is parallel to the time axis with magnitude c. This is because we said that the 4-velocity initially had 0 x component. So we've confirmed that a world line of an object undergoing constant proper acceleration is indeed a hyperbola, parameterized by hyperbolic sine and hyperbolic cosine, with the alpha parameter indicating how strong the observer's constant proper acceleration is. The last thing I want to talk about is an interesting phenomenon related to acceleration in special relativity called the Rindler horizon. The Rindler horizon phenomenon is named after the physicist Wolfgang Rindler. Let's say that Einstein is stationary and Rindler is undergoing constant acceleration on a hyperbolic world line. And let's say that Einstein sends beams of light toward Rindler at constant intervals in time. We see that the first few light beams reach Rindler with no problem, but after a certain point, the light beams will never catch up with Rindler. Because Rindler is going faster and faster, he is actually able to outrun beams of light when they are sent from far enough behind him. Basically, any beams of light that are sent from this shaded region of spacetime will never reach Rindler. This means that there is a boundary behind Rindler where everything behind the boundary appears as complete darkness to him, because light from behind the boundary will never reach him. This boundary is called the Rindler horizon. Nothing from behind the Rindler horizon, not even light, can ever reach or influence Rindler. In some ways, this is similar to the horizon of a black hole, where nothing behind the horizon of a black hole can ever get outside of it. In this case, nothing that is sent from behind the horizon can ever cross through to the accelerated observer's side of the horizon. However, unlike black holes, the Rindler horizon is ultimately artificial. As soon as Rindler stops accelerating, the light beams will catch up with him again. Black holes, on the other hand, are actually physical and can't be removed by changing reference frames. An interesting question to ask is, how far behind Rindler is the Rindler horizon? We can figure this out by looking at the various position basis vectors along Rindler's world line and measuring the distance to the Rindler horizon, parallel to these position vectors. Since all of these position vectors meet at the origin, this is the same thing as just measuring the length of Rindler's various 4-position s vectors. If you recall, for our hyperbolic world line, the space-time interval s.s is a constant number for all time, negative the square of c squared over alpha. This means that when Rindler looks back, parallel to his x-position basis vector, he will observe a proper distance L0, which is the square root of minus s.s. This means that Rindler sees a horizon, specifically the origin, to be a constant distance of c squared over alpha for all time. So what is normally a distance that gets larger and larger from the point of view of Einstein's stationary frame becomes a constant distance in Rindler's frame because of the increasing effect of length contraction. So the Rindler horizon is always a constant distance behind Rindler, even though he is always moving forward. This means that a beam of light released on the Rindler horizon, for example, a beam of light released at the origin of our space-time diagram, is always a constant distance behind Rindler. The speed of the light beam, according to Rindler, is actually 0. So the postulates of special relativity say that the speed of light in a vacuum is always c equals 300 million meters per second in all inertial reference frames. But in non-inertial reference frames, the speed of light can have different values, even 0 in some cases, as we've seen. It also turns out that Rindler will never see any objects fall behind his Rindler horizon. Anything that gets close to the horizon will experience so much time dilation from Rindler's perspective that it will almost freeze in place. It will very slowly approach the horizon, but it will never cross it from his perspective. Remember, time dilation means that moving clocks run slow. So from Rindler's perspective, any objects that approach the Rindler horizon will have such significant time dilation that they will almost freeze in place. The object will very slowly approach the horizon, but never cross it from Rindler's perspective. So to summarize this video, we found that a curved world line is a series of instantaneously inertial reference frames, where every point on the world line has a different inertial frame, where the time basis vector is tangent to the world line, and the position basis vectors are Minkowski orthogonal to it. We also learned that for velocity and for acceleration are always Minkowski orthogonal to each other, with a dot product of 0. We learned that proper acceleration is the acceleration measured on an accelerometer carried by an observer, and we learned that the condition for constant proper acceleration alpha is a dot a equals negative alpha squared. This assumes that acceleration is only in the x direction. And we also learned that objects traveling with constant proper acceleration have a hyperbolic world line according to inertial observers. We also learned that accelerated reference frames can actually outrun beams of light, and there is a constant distance behind accelerating observers called the Rindler horizon, and the distance of the Rindler horizon behind the observer only depends on the value of the acceleration, alpha, and the speed of light. Light beams sent from behind this horizon can never reach or influence the accelerated observer. And light beams that are sent exactly on the horizon will appear to be frozen in space from the perspective of the accelerated observer. In this video, we're going to continue.
I think that's it for me today. I'll probably be back tomorrow or some other time to continue the course on the cleaning data. I think it's cleaning data. Continue this course on Kaggle. So see you.